In addition to describing things like mean, median, standard deviation, and IQR, it's also important to be able to talk about where a specific data point lies within a distribution. And there are a couple of ways we do that, and the first one is one that probably is very familiar to you. It's percentiles. So you've all taken tests like the TCAP, the Explorer, the ACT, etc. And many of them also often return with percentiles for you. For example, you were in the 98th percentile, or you were in the 97th percentile, or the 65th percentile, or the 87th percentile. Okay, so this is what a percentile actually is. A percentile measures the percent of data values that were lower than a particular one. So, for example, if you were in the 97th percentile, that means 97% of people scored lower than you did on the test. Okay, so the larger the percentile, the better you did. Okay, so on a test, like on the one we just took, if you earned a 97%, does that mean that you were in the 97th percentile? And the answer is no, not necessarily. And sometimes it could work out that way, but the student's percentile and the percent correct are not the same. So if you, for example, were in a class of 5 and you scored a 98, but someone above you, or someone scored 100, then you are position 4 out of 5, which means that there were 3 people out of 5 lower than you are, which puts you in actually the 60th percentile. So let's look at some examples of this. Here is a dot plot of scores, and this is actually from Ms. Hines' first test from last year. And if we look at the percentiles of the following students, so here we have everyone's percent correct scores. There are actually 76 people in this dot plot. Okay, 76 points in this distribution. And if we're looking for a student who earned a 93, okay, 90, 91, 92, all of these people earned a 93. Okay, something very important when you're figuring out percentiles. When you have the same number of people who earn the same thing, these people all have the same percentile because they all earn the same score. So what we do is we use all the people lower than 93. So all of these people, and when you count it up, you actually get there are 66 people who scored below a 93. So to find my percentile, I would say 66 out of 76. Okay, and then I'm going to round. Percentiles are always whole numbers. You should never get any decimals. So after I round, I end up with these students are in the 87th percentile. And you can write it out or you can abbreviate it like this. Okay, so if I look at the student who earned an 86, those are all of these students right here. So if I count everyone below them, I end up with 34. And when I say 34 divided by 76, I end up with the 45th percentile. And then a student who earned a 79, that would be these students right here. And when I count all the ones below them, I end up with a 13. And so I say 13 out of 76. Then I round to the nearest whole number. It's the 17th percentile. So you always round to the nearest whole number. Always calculate values that are below divided by the total number of values. So that gives you the percent of people who are below you. One thing to note, you will not always see percentiles calculated this way. Sometimes you see percentiles where they include the people in that category as well. So if we were calculating it based on that definition where it's at or below a certain value, then this one where we're doing 79 instead of 13 would be 14, 15, 16, 17, 18, 19 out of 76. There is no specific way to do it. In statistics, oftentimes there are a couple different ways to do things, and there may be an agreed upon way and there may not. In this case, there is not an agreed upon way. You can either calculate it by just using the values below and say that that percentile is the percent of people below, or you can say that it is percent at or below and include the data points at that specific place. We are going to, just for consistency's sake, stick with the definition below. We are not including the values when we add. So do not include the values. On the AP test, they will take either one. And if it's a multiple choice question, then only one of the options will be there, and it'll be, they're not going to try and trick you. We are not going to include the data values. So when I say I want to know the percentile of students who earned a 93, I am not including the people at 93. Okay, so let's look at some more percentiles. These have to do with wins in Major League Baseball. This is a stem plot of the number of wins for each of the 30 Major League Baseball teams in 2009. Okay, the Colorado Rockies won 92 games. That would be this team right here, 92. Which means that 24, if I count all of these numbers below them, 24 out of the 30 teams had fewer wins than they did. So if I say 24 over 30, and then I round to the nearest whole number, I get the 80th percentile. So if I was interpreting this, I would say 80% of teams won fewer games than the Colorado Rockies in 2009. Or Colorado Rockies won more games than 80% of the teams Major League Baseball in 2009. Okay. So if I'm looking at the New York Yankees, that's this team. And you would say, oh, they're the top one. They must be 100%. But that's not the case because, remember, I don't include these. So I am actually never going to have 100% because I'm never going to include the very top team in my calculation. So I am never going to have anyone in the 100th percentile. Not by our definition. So that means that 29 out of the 30 teams did worse than the Yankees, and therefore they are in the 97th percentile because they did better than 97% of other teams. Kansas City Royals and the Cleveland Indians. That are these two teams. They have the two same number. So I start with what's below them and I count. So 1, 2, 3. So these two teams are better than 3 out of 30, which puts them in the 10th percentile. So those are ways that we talk about, one way that we talk about your location within a distribution, and talking about one data point in relation to all the others. Okay. Another way that we can look at your position in a data point's position is with a cumulative relative frequency graph. Cumulative relative frequency graphs show a data point or show the data in relation to their position with everything, with all the other data, as well as the total. Okay, and I'm actually going to scroll down a little bit. I can get it on the screen. Okay, so this is a cumulative relative frequency graph. Median household income. So what this is for the 50 states and the District of Columbia, and it's difficult to see there we go, x-axis, so I'm going to scroll down some. Okay, so what we can tell from this, and I know I left a question unanswered, but I want you to be able to see the graph to answer it, is that right here, notice how this goes from 0.0 to 1, because we're relative frequency, so that's like proportions and percents. My graph will always start at 0 and always go up towards 1. And what relative frequency does is, remember when I have a frequency chart, so my data values are over here, counts are on this side, and then to turn that into relative frequency, I divide each individual count by the total, and basically I get the percentage of values, okay, the percentage of that data value out of the whole data set. So frequency relative to the rest of the data. What this does is it takes it and adds it up. So at 35 we were right at 0.0. At 40, we were right at maybe 0.05. At 45, we're at around 0.2, but this right here is not just the relative frequency of 45. This is the relative frequency, or the percentage, or the proportion of 45 plus 40 plus 35. And the next point is 50 plus 45 plus 40 plus 35. So it just keeps going and going and going. And for the ones in my class, when we looked at the graphs, the bad graphs, and we saw the graph from BP, that is what they had. They had a cumulative, theirs was cumulative frequency, but cumulative relative frequency is the same thing except you use proportions. It adds on from the things before it. So what did the slopes tell us? Well, I can see right here that since I know this point includes this one, if the slope is shallow, I didn't add much. So there was not a lot of data in between those 2 points. If the slope is very steep between 2 points, then that means that my data increased a lot from one point to the next. So the slope actually tells us how much it increased from one point to the next, because the data values tell us how much it's increased total. Okay, so let's look at this graph. California with a median household income of $57,445 is at what percentile? Okay, that's another thing that these cumulative frequency graphs are very helpful for. They tell us the percentile just by looking at the graph. So if I go to this and I go to about 57,455, it's about right here. And I go straight up, and then I look straight across, and I get about to 0.78 maybe. And since my cumulative relative frequency means that all these points added together until I get to this are about 0.78 of the whole thing, that means that this is the 78th percentile. Okay, so that's how we found percentiles based on cumulative relative frequency graphs. Let's think about this. If I find the 25th percentile, I'm going to go, okay, percentile is basically percent less than, which is basically cumulative relative frequency. So I go to the 0.25. So this right here is the percent less than 25%. And when I go down, that's a little over 45. So maybe 46. Notice that right here means that from here, 25% of my data is less than this value. There is another value that we have where we say 25% of our data is less than that value. We use it with box plots, and it's quartile 1. So your 0.25 on your cumulative relative frequency corresponds to Q1. So hopefully you realize that 0.75 is going to correspond with Q3. And then that 0.5 would correspond with your median. So I can find the median of my data set by going from 0.5 and going straight over. That'd be around 50. Okay, and where the graph is the steepest tells us that from here to here, where it's the steepest, that's where we saw the most increase. So from 45,000 to 50,000, we added the most people to our household income. So that is the largest relative frequency difference in relative frequency is between those two. Okay, something else that we should mention is that oftentimes you will hear this kind of chart referred to as an ogive. So if you hear someone say ogive, or you see the word somewhere, that means cumulative relative frequency graph, which tells us all sorts of information. It just means that this is the frequency of 35, this is the frequency of 35 plus 40, and I keep going up. Okay, so let's look at these check your understanding questions really quickly. So the first one is multiple choice. And remember to stop the video and answer these questions yourself and then try and come back and watch. The answer to number 1 is C. The answer to number 2 is that her daughter weighs more than 87% of children her age and is taller than 67% of girls her age. Number 3 means that about 65% of calls lasted less than 30 minutes, and about 35% of calls lasted 30 minutes or longer. And notice that with number 3 here, even though I didn't write out the answer, that 65%, which is the percentile, how many lasted less than that, and 35%, which was lasted that or longer, add up to 100. So if ever I do the percentile and then I do the percent that or longer, they always should add up to 100. And number 4, the first quartile, is about 14 minutes because I have to look at where the 25th percentile is. And then the third quartile, where I look at the 75th percentile, is about 32 minutes. When I subtract them, my IQR, it's about 18 minutes. There is one more thing that we need to talk about in terms of measuring position, and that are z-scores. Z-scores are also known as standardized scores, know both names, and they are really important because they help us figure out if a distance from a mean is good or bad. So for example, I could say that Susie was 6 points above the mean on her test. Okay, that could be a really good thing if 6 points above the mean was the highest grade. So, you know, maybe a lot of people had 1 point above the mean, and some people had 2 points above the mean, but Susie had the best at 6 points. Or it might not be so good if maybe 6 points above the mean is only one data value above the mean, and everyone else did better than she did. So in order to have a way to talk about it, where it actually means something and tells us, you know, how well she did in relationship to everyone else, we use a standardized score. Okay, standardized scores are calculated using the data point, the mean, and standard deviation. And so what I do to calculate a z-score, I take the data point, I subtract the mean, which is either mu or x bar, depending on if it's a population or a sample, and I divide by the standard deviation, which is either sigma or s, depending on a sample or a population. So what this does is this part tells me my distance from the mean, and then by dividing by the standard deviation, I can figure out how far it is in relation to everyone else, because that gives me a measure of spread. Z-scores do not have units. because since standard deviation has the same units as these, when I subtract, my units stay the same, but then when I divide, my units cancel. When I divide, my units cancel. Okay, and what does the sign of the standardized score tell me? Since I am subtracting my data value minus the mean, if it's positive, that tells me my data point was larger. So the point is above the mean. If it's negative, that means my mean was larger, which means my point is below the mean. Okay, so let's look at a couple more examples. One is the home run king. Okay, the single season home run record for Major League Baseball has been set 3 times since Babe Ruth hit 60 home runs in 1927. It's been set by Roger Maris, Mark McGwire, Barry Bonds, and in an absolute sense, Barry Bonds has had the best performance. However, baseball historians suggest that hitting home runs now is easier than, for example, when Babe Ruth or Roger Maris did it, because of the quality of batters, the quality of pitchers, the different makeup of baseballs, the different dimension of the ballparks. You could always consider the fact that maybe they used performance-enhancing drugs, say different bats. So to make a fair comparison, we don't just want to compare the number of home runs, but we want to compare to how those players did in relation to other players their same year. So we can calculate their standardized scores and see how well they did in their year. So here are our years and our players and our amount of home runs, the mean number of all home runs hit, and the standard deviation of home runs. And so we can figure out their standardized scores. So if we want to calculate a standardized score for each player, here we would say data point minus the mean divided by the standard deviation. We would do the same thing here, same thing here, same thing here. Okay, notice that throughout the years, not only did the number of home runs go up, the mean number of home runs went up as well, and the standard deviation went up and then stayed pretty close to the same. So if we actually do the math here, Babe Ruth has a z-score of 5.44, meaning that he was 5.44 standard deviations above the mean. Okay, so if the standard deviation is 9.7, he was that 5 times this above the mean. Roger Maris had a z-score of 3.16. McGwire has one of 3.87. And Bonds has one of 3.91. Okay, so notice that these get better as they go in the modern era. But look how big Babe Ruth's z-score is. Okay, that means these people did better than 3 standard deviations above their mean. He did 5. That is an outrageous amount, and it is way far out there, meaning that very few people, maybe one, maybe none, did better than he did that year. So we can say that even though he has not hit as many home runs as Barry Bonds or Mark McGwire or Roger Maris, Babe Ruth's home runs probably meant more because they were harder to come by, which is why he is so far above the mean in terms of standard deviations. Okay, so in 2001, Arizona Diamondback Mark Grace's home run total had a standardized score of negative 0.48. So if we interpret that value, that means that he was 0.48 standard deviations below the mean. 0.48 standard deviations below the mean. And then it asking us to work backwards and find the total number of home runs hit. Well, I know my formula, and I know it's from 2001, so we have a mean, and we have a standard deviation. So some value, which is the number of home runs he hit, minus the mean, divided by the standard deviation, is going to give us our z-score. We know our z-score is negative 0.48. So then I just have to solve for x. If I solve for x, then I multiply by 13.2 and then add 21.4. And we get an actual value of 15.06. So he hit 15 home runs. So you set up your z-score value, but this time instead of plugging in x, we plug in z-score, and then we can work backwards to get the x. So if we go back to the stem plot for Major League Baseball, and we want to talk about the z-scores there, we go back and we have to know that year the mean number of wins was 81 with a standard deviation of 11.4. But since we had all the data, we could have calculated that out with stuff that we learned from Chapter 1. However, since it's right here, we can just use the data they have. So, if I have the New York Yankees with 103 wins, their z-score should be positive and should be high because they were the top team. So, to find what it is, 103 minus the mean divided by 11.4, and that gives me a z-score of 1.93, meaning they were 1.93 standard deviations above the mean number of wins that year. Okay, and then I look at the New York Mets, who had 70 wins that year, and I say 70 minus 81, and I can already tell that my z-score should be negative because I'm underneath the mean. So if it does not come out to be negative, then I know that some math has gone wrong somewhere. So I get negative 0.96, which means they were 0.96 standard deviations below the mean. Okay, so those are z-scores. It is very important on the AP test to make sure that you show your work on z-scores. Okay, you need to show this formula when you find a z-score. They will be looking for the formulas. Show your work out just like this. Okay, so now pause the video, answer the check your understanding questions, then turn the video back on and see how you did. Okay, for number 1, we should have gotten a formula that looks like z equals 65 minus 67 over 4.29, which is negative 0.466, which means that her height is about 0.47 standard deviations below the mean height of the class. Notice that when I say this, I'm saying it in context. I am not just saying 0.47 standard deviations below the mean. It's below the mean height of the class. Okay, for number 2, Brent's z-score, 74 minus 67 over 4.29, and I get 1.63, which means his height is about 1.63 standard deviations above the mean height of the class. Okay, and then we have number 3, and he's a member of the school's basketball team. And on just the team, that means his z-score is negative 0.85. They give us the mean, and we know his height already, so we need to find the standard deviation of the basketball team. Well, we know that his height was 74, and the mean height of the team is 76 inches. We just need to know standard deviation, and I can use the population symbol because we're looking for the population of the entire team. So I need to multiply by negative 0.85, multiply this, and then divide by negative 0.85. Okay, notice I can tell it's going to be positive because this is negative and this is negative. So that's good because all standard deviations need to be positive. And I get about 2.35. And now that I'm solving for standard deviation, I have a unit. It's the same unit as my data points, inches.